So we want to start off with the question, or the idea, we want to take derivatives of trigonometric functions. So the question we want to start with is, well, what is the derivative of sine? So if we grab our graphing device, and let's go ahead and graph one period of the sine function. So we go sine x. And let's change our window. We're going to go one period is from 0 to 2 pi. And we'll leave our x scale as 1, but let's zoom in a bit. So let's make our y min -2 and our y max +2. And if we graph, we get something that looks like this. So if we remember, our key idea for a derivative is derivatives represent slope. So if I were to look right here, and I wanted to approximate that, so on my square graph here, if I look at my tangent line, that appears to have a slope of 1. And then, as we know right here, at our maximum, it has to stop, so it's going to have slope 0. Then we kind of do the same thing here, and we look again. Here we're going to have slope -1. And down here we're going to have slope equal to 0 again. And then lastly, right here, it seems like we're getting back to where we just started, and we're going to have slope equal +1. So it appears that our function is going to, its derivative, so f prime, whatever it's going to be, if we test some different values, we have x and we have f prime of x, so at 0 we should get 1. At the maximum we would get pi over 2, we should get 0. When we come back down to pi, and it looks like we have -1, and then at 3 pi over 2, we get 0, and we come full circle back to the beginning at 2 pi, we circle back to 1. Well, what is the cosine of 0 equal to? 1. What's the cosine of pi over 2? 0. What's the cosine of pi? -1. What's the cosine of 3 pi over 2? 0. And the cosine of 2 pi is indeed 1 because it's 2 pi periodic. So based on this qualitative graph, we're going to hypothesize that the derivative of sine should be cosine. That the derivative of sine so this is not a proof, right? We just looked at a graph, eyeballed some slopes, but it seems reasonable based on the data that we came up with. All right, so our goal is we actually want to show that that's going to be the case. So as we talked about last time, our goal in this chapter is to develop theorems so we don't have to use first principles. But if we ever need to show something, our atomic building blocks are always first principles. And when we say first principles, we mean the limit definition. So before we can use the limit definition, we're going to need to prove some propositions or baby theorems that are going to help us. So the proposition that we're going to need is that the limit as h goes to 0 of the sine of h divided by h is going to equal to 1. So unfortunately, we can't just directly use the evaluation theorem, because if I plug in h equals 0, I divide by 0. That's a problem. And so we're going to have to find an indirect method to do this proof. So to get started, we are going to use some geometry. On our handout, we have the unit circle graphed, and we have a reference triangle in quadrant 1. So we're going to do our proof in quadrant 1. You can do a similar argument in any of the 4 quadrants, and this does hold. But since we are taking the limit as it goes to 0, the only quadrants we'd really be concerned with is quadrants 1 and quadrants 4. So you're going to get a similar argument if you reflect this across the x-axis. Everything works out exactly the same by symmetry. So we're going to go back to some of our base definitions. So what is the sine of theta by definition? Well, sine theta is opposite over hypotenuse. And recall, we're on the unit circle, so that'll be helpful. So if we look at our reference angle theta here, we have this triangle right here. So our opposite is going to be the line segment BC over our hypotenuse, which is going to be the line segment OB. But we're on a unit circle, so if we're on a unit circle, what do we know the radius is? R has to be 1, right? So this will tell us then that sine theta is equal to BC. Well, we know that because that's really just saying the sine of theta is equal to y, right? Because the length of BC would be the y coordinate of that point. Okay, so that's nothing new. We now want to make a chain of inequalities. So we know that the sine of theta is equal to BC. And if we look at BC right here, I'm going to claim that BC has to be less than or equal to AB. Well, AB is this line segment. So why is BC less than AB? Well, if we look at this triangle that we have right here, here's BC, CA, and AB. AB is the hypotenuse of that triangle. The hypotenuse is always the longest side of any triangle. So the length of AB, therefore, must be greater than the length BC. Right? That's all we're saying, that the hypotenuse is the longest side of that triangle. Well then, if we're looking at this line segment, the hypotenuse, I'm going to claim that it is shorter than the arc of the circle that connects these 2 points. So why would that have to be true? Well, what's the shortest distance between 2 points in Euclidean space? A straight line, right? So if I have a curved line, or a curve, it must therefore be longer than any line that connects the same 2 points. So that tells me that the arc AB is bigger than the line segment AB. But in radians, the length of that arc is the definition of the angle theta. Remember, radians is the distance that you would walk along the circumference of the circle, starting at A and ending in B. So by definition, then, arc AB is theta in radians. So now, if I have sine theta is equal to BC, but BC is less than AB, which is less than arc AB, which is equal to theta, combining all of those things together, we get that the sine of theta must be less than or equal to theta. Okay. Interesting. But all of those statements hold, so that must be true. And it is good to remember that this is in radians. Okay. Well, if I have this inequality, and I divide by theta, and I divide by theta, this tells me that the sine of theta divided by theta is less than or equal to 1. Okay. So we know that the biggest that ratio can be is 1. All right, so now we're going to refer to this statement. I'm going to label it for later use. We will call this fact 1. All right, so now we're going to do some more reasoning with this picture. So now we want to talk about the tangent of theta. So I come back up to my diagram, and by definition, what is tangent? Well, tangent is opposite over hypotenuse. So we're going to be talking about this triangle right here. So using this, the tangent of theta is going to be AD divided by OA. But OA, this distance right here, is once again on the unit circle. So if it's on the unit circle, what does its measure have to be? That's the radius of the unit circle. So the radius of the unit circle is 1. So this tells us that the tangent of theta is equal to AD. All right, so we're going to make some claims. So once again, we know that theta is equal to, by definition, the arc of AB. That's the same thing that we did above. That's just theta in radians is equal to AB. And I am going to claim that arc AB is less than AD. So let's think about that for a minute. Why would that statement be true? Why is this distance right here going to be less than this distance right here? Why don't you guys think about that for a minute? We'll assume it's true for right now, but I know it's been a long time since we've done geometry, but I'll let you guys ponder that for a moment. So, assuming that statement is true, we now have that theta is less than or equal to AD, but AD is equal to tangent theta. So connecting all of these things, we then have the following. Theta is less than or equal to tangent theta. Tangent is the same as sine divided by cosine. So if I have theta is less than or equal to sine theta over cosine, I can multiply by cosine theta over theta and multiply by cosine theta over theta. And when I do that, my thetas reduce out and my cosines reduce out. And that gives me then that cosine theta is less than or equal to sine theta divided by theta. And I am going to refer to this statement as fact 2. So fact 1 says sine theta over theta is less than or equal to 1. And fact 2 says sine theta over theta is greater than or equal to cosine theta. So by combining, we get the following. Cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1, right? That's fact. The inequality on the left, these two, that's fact 2. These two together is fact 1, right? Well, now we've set ourselves up perfectly to use the squeeze theorem. So by the squeeze theorem, we have the limit as theta goes to 0 of this, and the limit as theta goes to 0 of this, and the limit as theta goes to 0 of this. Well, cosine is continuous, so what's the limit as theta goes to 0 of cosine? Well, cosine of 0 is 1, is less than or equal to the limit as theta goes to 0 of sine theta over theta, and the limit of a constant is just the constant, so is less than 1. So then, if that limit is less than or equal to 1, but that limit is also greater than or equal to 1, what's the only choice for the limit? It must be exactly 1. because if it's less than or equal to 1, but also greater than or equal to 1, the only value that's left for it is the value of 1. So we've proved that that limit is exactly equal to 1. All right. So I'll rewrite it now in terms of h's instead of thetas. So the limit as h goes to 0 of sine h over h is equal to 1. There is another limit which we are not going to go through, but you can use the same circle and the same type of reasoning to get the same answer. The limit as h goes to 0 of cosine h minus 1 over h is equal to 0. We are going to need both of these things in order to find our derivatives. Okay. So let's go ahead and prove our first theorem. As we suspect, it turns out it's true that the derivative of sine is going to be cosine. So to prove it, we have to start with first principles. So y prime is going to be equal to the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. And we need to evaluate this limit. So unfortunately, once again, we can't just plug in h because we would divide by h. So we need to do some work in order to eliminate that h from the denominator. So to help us out, we're going to use a trigonometric identity. So the sum identity for sine is, if we have the sine of x plus h, it is equal to sine x cosine h plus sine h cosine x. And so that's our standard sum identity for our sine function. So replacing sine of x plus h with what it is equal to, we have the limit as h goes to 0 of sine x cosine h plus sine h over cosine x. And then we'll do term-wise division, splitting this into two fractions. So we can then evaluate each of these limits separately, because the limit of the sum is the sum of the limits. So we have the limit as h goes to 0. And now we can factor out anything that doesn't depend on h. So in our first one, the sine of x doesn't depend on h. So we get sine x, it's constant with respect to that limit. So we pull it out, and we get, I'm missing a piece. You know what, let's back up. I did too many steps at once. Let's be more clear. Limit as h goes to 0, we have our, I'll write this down again, sine x cosine h plus sine h cosine x minus sine x, that whole thing over h. Now let's break it up into the two parts. So if I take this piece right here and I pair it with this piece right here, I'm going to get the limit as h goes to 0 of the sine of x cosine h minus sine x all over h plus, now if I take this piece right here, I'll have a second limit, the limit as h goes to 0 of sine h cosine x all over h. All right, so now let's factor out what's constant with respect to h. So our limit depends on h. So x is a constant, so I can factor out my common factor of sine x from each of these. And that gives me sine x times the limit as h goes to 0. And then inside the limit, I am going to have cosine h take away 1 over h, plus our cosine is constant here, so we take it out with respect to that limit, and the limit as h goes to 0 of sine h all over h. So now we're finally ready to use our propositions. So what's the limit as h goes to 0 of sine h over h? 1. And what's the limit as h goes to 0 of cosine h minus 1 over h? 0. So this limit goes to 0, and this limit goes to 1. So that gives us sine x, so y prime is equal to sine x times 0 plus cosine x times 1. Well, anything times 0 is 0, so then at the very end, what do we end up with? Y prime is equal to cosine x times 1, which is just cosine x. So the derivative of sine is indeed cosine. So from now on, never, ever, ever, ever use the limit definition. We've proved it, right? So at the end of the day, when we ask what's the derivative of sine, what are you going to tell me? Cosine, right? Similarly, if you're interested, you can do it yourself using those same two propositions. The derivative of cosine is going to be negative sine. And both of these are on that summary sheet for our derivatives. So if we have y equals cosine x, then y prime is equal to the negative of sine x. All right. Let's go ahead then and do some examples. So find the derivative of y equals cosine x over x squared plus 1. So what rule are we going to need to use? It's going to be the quotient rule. So we identify our f and we identify our g. So f is going to be cosine x, and g is going to be x squared plus 1. So to use our quotient rule, we need to know f prime and g prime. So we just found out the derivative of cosine is going to be negative sine, and the derivative of x squared plus 1 by the power rule, the derivative of x squared is 2x, and the derivative of a constant is 0. So then g prime is going to be 2x. Our quotient rule says y prime is equal to g f prime minus f g prime all over g squared. So that gives us x squared plus 1 times negative sine x minus f, which is cosine x, times g prime, which is 2x, all over g squared, which is x squared plus 1 quantity squared. So cleaning up just a little bit, we then have, bringing our minus all the way out in front, negative x squared plus 1 sine x minus 2x cosine x all over x squared plus 1 squared. And that would be our derivative of cosine x over x squared plus 1. So just like we did last time, we have to find our derivative using the quotient rule. So for the quotient rule, we identify f, we identify g, then we find f prime and g prime and plug into our quotient rule. All right, it's now your turn. So I want you guys to go ahead and find the derivative of y equals x squared sine x. All right, so we identify our f and our g. Our f this time is x squared, and our g is sine x. So then f prime would be 2x, and g prime is going to be cosine x. And when we have a product, we know the product rule is going to be equal to g f prime plus f g prime. So that gives us sine x times f prime, which is 2x, plus f, which is x squared, times g prime, which is cosine x. So finally, we end up with 2x sine x plus x squared cosine x. And that would be our y prime. So once again, we identify that we have a product, so we select the product rule. We identify f and g, find f prime, g prime, and then at that point it's just plug and chug, put everything into the appropriate formula, and we are done. All right, so let's take a look at our next one. So we have c is y equals tangent. Well, we only figured out the derivatives for sines and cosines, but luckily we know what an alternate definition for tangent is. As we used before, one of the other definitions of tangent is that it is sine theta over cosine theta. Well, that would represent a quotient. So my f would be sine theta, and my g would be cosine theta. So then f prime would be cosine theta, and g prime, the derivative of cosine, is negative sine, so negative sine theta. So using our quotient rule, we have y prime is equal to g f prime, so cosine theta times cosine theta, minus f g prime, so sine theta times negative sine theta, all over g squared, which is cosine squared theta. So simplifying, we get cosine squared theta. Negative sine times negative sine is positive sine squared theta, all over cosine squared theta. But sine squared plus cosine squared equals to what? is equal to 1, and that's the Pythagorean identity. So then y prime is equal to 1 over cosine squared theta. But the reciprocal identity for cosine, 1 over cosine theta, is equal to secant theta. So the more common way to write this is y prime is then equal to secant squared theta. If you go and look on your derivative handout, you will also note that that derivative is present, right? So the derivative of tangent is secant squared. Webasine will also accept 1 over cosine squared, right? They're the same thing. So 2 different ways to write the same answer. That's one thing about Webasine, as I've been mentioning, is it's very, very forgiving of equivalent forms. So when I write secant squared, that's fine. If you want to write 1 over cosine squared, that's fine too. It's not going to care. Neither will I. So they are both the derivative of tangent. All right. So the next one is very, very interesting. So our next problem is this guy. And we're going to have the product rule, but this time what's different is there's 3 factors. So the first step in using the product rule is we need to identify our f and our g, right? So f is going to be theta squared, and g is going to be sine theta tangent theta. So then we calculate f prime. So the derivative of theta squared is going to be 2 theta. So that's power rule. But now we need to take the derivative of g, and what do we notice? Well, g is sine theta times tangent theta. This is a product. So we have to push in another level. And we're going to have to use the product rule again. But inside this new product rule, we can't see anything that's outside. What's my new f and what's my new g? F would be sine theta. G would be tangent theta. So now at this level, we have to calculate f prime and g prime. So f prime, the derivative of sine is cosine. And we just did this one. The derivative of tangent is secant squared theta. Okay, so now we can calculate what our derivative is. So our derivative g prime, not the same g that's in here, but this g, is going to be g f prime. So it's going to be tan theta cosine theta plus fg prime, so sine theta secant squared theta, right? And we can simplify that up a little bit if we wish, because as we know, tangent is sine over cosine times cosine plus sine theta, and this is 1 over cosine squared theta, So in our first one, the cosines reduce out. And we get G prime is equal to, we have sine theta, plus sine over cosine is tangent, and 1 over cosine will be secant. So we're going to get secant theta, tangent theta. So that's our derivative here, G prime. So now we have to pop back out a level because the derivative of our original function y prime is going to be G f prime plus f g prime. So G, our original G, is sine theta tangent theta. Times f prime, well, f prime is 2 theta, plus f, which is theta squared, times our g prime, which is what we just found out here, sine theta plus secant theta tangent theta. And that would be our derivative, right? So let's kind of recap what happened here. Since we had more than 2 products, we had to use the product rule twice because we had 3 factors. So we identified f, and we identified g. F prime we could directly calculate, but then we had to push down a level and use the product rule again. So in our g, we had sine theta tan theta, so that became our new f and our new g. We kind of ignored everything we were doing. We pushed down a level, did the product rule again, and finally when we finished that product rule, we had the g prime that went with our first product rule. Then we could do the formula there again. So we're going to be pushing down and then popping back up after we finish. So when we go down another level, i.e. we use another rule inside a rule, we just ignore what's going on outside of it for a while, finish that rule, and then when we're done, we pick up where we left off. So we got to hand off to this new process, finish it, get the result back, and then go back to the original rule. And whenever we have 3 factors in a product rule, we're going to do this, or something similar in a quotient rule. If you had a product in either the numerator or denominator, you would have to do the same thing, right? So we can mix and match all of our rules together as we're doing this. All right. Let's take a look at our next example. So find the equation of the tangent line and the normal line to y equals, or f of x equals, sine theta times cosine theta. So one thing we do have to remember is, what is the normal line again? The normal line is perpendicular to the tangent line. So our slope is going to be the negative reciprocal of the slope of the tangent line. All right, so the first thing we need to do is find our derivative. So if that's the case, we have a product rule. F is going to be sine theta, G is going to be cos theta, so then F prime is cos theta, and G prime is negative sine theta. So then F prime of X is going to be G F prime, so cosine squared theta, plus F G prime. So sine theta times negative sine theta, instead of plus, it's going to be negative now, negative sine squared theta. So now we need to figure out our slope. So M1, our slope of the tangent line, is going to be F prime evaluated at pi over 6. So that's going to be the cosine squared of pi over 6 minus the sine squared of pi over 6. And now we need to remember, well, what is the cosine of pi sixths? So if we look on our unit circle, that's in quadrant 1. And if we go to our angle pi over 6, we're going to have our 1, 2, square root of 3 triangle. So cosine is adjacent over hypotenuse. So that's going to be root 3 over 2 squared minus sine, which is opposite over hypotenuse, which is going to be 1 over 2 squared. So this is going to give us that our slope of the tangent line is the square root of 3 squared is 3, square root of 2 squared is 4, minus 1 squared is 1, minus 2 squared is 4. So 3/4 take away 1/4 is 2/4, which reduces to 1/2. So the slope of the tangent line is 1/2, and the slope of the normal line is M2 is equal to negative 1 over M1. In this case, that's going to be negative 2, because it's the negative reciprocal of that slope. Also note, we didn't have to do this evaluation by hand, right? You could just put that in your calculator. Sine squared, cosine squared, pi over 6, right? Subtract the 2, and you'll get what you need. And your calculator would tell you 0.5, right? And it'll give you the same value. So you can always use your calculator. So then we have our tangent line, and we have the normal line. So if our slope for the tangent line is 1/2, and it has to contain our point, and the point that was given is pi over 6 and root 3 over 4. And then we have to do the same thing here, but our slope is negative 2, and we have pi over 6, and the point is still pi over 6 and 3 pi over 4. So to find the equation of a line, we use our slope. So y equals 1/2 x plus b, and we need to find b. So we have root 3 over 4 is equal to 1/2 times pi over 6 plus b. So root 3 over 4 is equal to pi over 12 plus b. We minus pi over 12, and we minus pi over 12, getting root 3 over 4 minus pi over 12 is equal to b. So finally, our line is y equals 1/2 x plus root 3 over 4 minus pi over 12. And that's going to be the equation of our tangent line. Okay, so now we rinse and repeat for our normal line. So we do exactly the same process, y equals negative 2x plus b, and we still have root 3 over 4 equals to negative 2 times pi over 6 plus b. So that gives us root 3 over 4 is equal to negative 2 goes into 6 3 times, so negative pi over 3 plus b. We add pi over 3, and we add pi over 3, getting b is equal to root 3 over 4 plus pi over 3. So the equation of our normal line is y equals negative 2x plus root 3 over 4 plus pi over 3. So that's the equation of our tangent line and the equation of our normal line to that curve at the point root pi over 6 and root 3 over 4. All right. Let's take a look at equation
to the normal line really quick.
Alright, so example 4, an elastic band is hung on a hook and a mass is attached to the lower end. When the mass is pulled down and released, it vibrates vertically. The equation of motion is s of t equals 2 cosine t plus 3 sine t, where t is measured in centimeters and t is in seconds. So find the velocity and the acceleration. So if s of t is the position function, velocity is the derivative of position. So v of t is going to be equal to s prime of t, and that will give us the derivative of 2 cosine t. The derivative of cosine is negative sine, so we get negative 2 sine t plus the derivative of sine is cosine. So we get 3 cosine t. So the velocity function is negative 2 sine t plus 3 cosine t. And acceleration is the derivative of velocity. So that would be v prime of t, which would also be the same as the second derivative of position. So differentiating our velocity function, the derivative of sine is cosine. So we would get negative 2 cosine t, and the derivative of cosine is negative sine. We get negative 3 sine t. And we could then factor out a minus sign, and we would get the negative of 2 cosine t plus 3 sine t. The reason that is interesting is this right here is s of t. So combining these two things, we get the following, that the acceleration function is equal to the negative of the position function. This is something that happens in physics that we describe as simple harmonic motion. So, simple harmonic motion, if an object is experiencing simple harmonic motion, its acceleration will always be equal to the negative of its position function. So basically it tells us that the restoring force is proportional to how far it's stretched away from equilibrium, because force is equal to mass times acceleration. So dividing the mass out. So when you see or hear about something in simple harmonic motion, it means it must satisfy this type of relationship. And that leads to simple harmonic motion. When you go and take your physics class after this, because I know Calc 1's a prereq for physics, you'll get to talk about this more in mechanics. But things that undergo simple harmonic motion will always have that relationship. Okay, so now the next thing it asks us to do is to graph position, velocity, and acceleration. Well, the easiest way to do that is to just do so on our calculator. So we go to our y equals, and let's go ahead and put our position function in. So position was given as 2 cosine x plus 3 sine x. And then our velocity is negative 2 sine x plus 3 cosine x. And then our acceleration is the negative of our position function, so we could just type that in as negative 2 cosine x minus 3 sine x. And let's go ahead and graph a couple of periods of this. So let's go all the way out to 2 or 4 pi, so change it from 2 pi to 4 pi, and graph. We're going to have to change our x or our y scale a little bit. Our graph was going off, so let's see, we have 3 and 4 were our, or 2 and 3 were our coefficients. So 2 squared plus 3 squared is the square root of 13. So square root of 13 is going to be less than 4. So let's go window and change our y min and our y max to plus or minus 4. And that'll make everything fit nicely onto our graph. I go position in orange, my position function is this wave. Velocity is going to be this one. And then acceleration is the reflection of position across the x-axis. So since orange was position, the green graph had to be acceleration because they are negatives of each other, or reflections across the x-axis. So that gives us a graph of our position, our velocity, and our acceleration. All right, so now question C says, when does the mass pass through the equilibrium position for the first time? So the equilibrium position is code for 0. So basically what it's saying is, when does the mass come back to the x-axis for the first time? So if the position is in orange, our equilibrium position, so remember our axes are time, and this is position. At least in terms of the orange graph, right? So our equilibrium position is going to be right here. So we need to find the x or t-intercept of the position function. So our position function is s of t is equal to 2 cosine t plus 3 sine t. To find the x-intercept, we're going to need to solve, essentially, s of t equals 0. So basically 0 is going to be equal to our position function. So it's been a while probably since we've solved trigonometric equations. So when we have both sines and cosines and we need to solve, oftentimes the strategy that we need to use is we're going to want to turn the sines and cosines into tangents, because we can't use the inverse sine right now because it would trap a cosine inside the inverse sine. The same reasoning holds for an inverse cosine. I couldn't get a cosine by itself and use the inverse cosine because it would trap a sine inside the inverse cosine, which we wouldn't be able to resolve. So what we're going to want to do is try to make a tangent function. So to do so, we're going to get our trig functions each on their own side of the equation. So I am going to subtract 2 cosine t from both sides, giving me the equation negative 2 cosine t is equal to 3 sine t. And since I'm trying to make a tangent, by definition, tangent is sine divided by cosine. So I'm going to divide both sides of the equation by cosine. But in the end, I also want tangent to be by itself, so I'm also going to divide both sides by 3. So on the left side, the cosines reduce out, and on the right side, the 3's reduce out. And this leaves me with negative 2 divided by 3 is equal to sine over cosine, which is tangent. So now I have the equation tangent is equal to, or tan t, tangent of t is equal to negative 2/3. So now I'm going to use the inverse tangent on both sides. So that's going to give me the tangent inverse of negative 2/3 is going to equal to the tangent inverse of tangent t. Well, the tangent inverse and the tangent, since they're inverses, are going to undo each other. So finally, I get t is equal to the inverse tangent of negative 2/3. Okay, so that's an exact answer, but we need something else. So let's ask our calculator. So make sure that your calculator is in radians if it is not. So negative 2 over 3, and we want to take the inverse tangent of this. And when I do so, my calculator gives me this value, negative 0.588. Let's go back and look at our graph. Something's not quite right. Because when I look at my graph here, my first x-intercept is right here. What do I know about that x value? What must it be? Positive, right? What answer did we get? Well, when we did it on our calculator, what did we get? A negative answer. Why did our calculator give us something negative? So we have to remember the following. The range of the inverse tangent is negative pi over 2 to positive pi over 2. And the inverse tangent function will only give us values in between those two numbers. In our case, we got 1 in the negative half because the actual solution that we're looking for is bigger than pi over 2, which means we are in the wrong period. So we need to recall the period of tangent is pi. So we need to add pi to our solution. So we go add pi, and that will shift us over to 2.55, which is exactly the answer we are looking for. So we need to remember when we're using trigonometric inverse functions, as we saw back in chapter 1, the range of those functions is important. And if we're not careful, we're going to get a correct answer, but it's going to be off by 1 or more periods to get what we're looking for. So we had to add a pi to shift that to the appropriate location. So the first time it passes through equilibrium is at about 2.55 seconds. So now the next question is, well, how far from equilibrium does the mass travel? So what is this asking us to find? So it wants, this is asking for the maximum of the position function. Right? Because if we go back to our picture, so our position function is in orange, it wants to know, well, what's the maximum distance that it gets away from the origin or the x-axis? Well, that's going to occur at several different places, right? Those are going to be all maximums. And what do we know has to happen at a maximum? What does its velocity have to be equal to? Well, remember, the velocity is in blue. So what is the value of its velocity when it turns around? Well, to be at a maximum, it has to go from increasing to decreasing. So at that maximum, what does its slope necessarily have to be? 0. So the slope, or the velocity, aka velocity, must be 0. So then, to resolve this, we're going to need to solve v of t equals 0. To find the time. Okay, so our velocity function is negative 2 sine t plus 3 cosine t. So we have negative 2 sine t plus 3 cosine t. And this needs to be equal to 0. So we're going to pull the same thing that we just did for the previous one, right? So we're going to minus 3 cosine t. We're going to minus 3 cosine t. That gives us negative 2 sine t equals negative 3 cosine t. And we are going to divide by negative 2 cosine t and divide by negative 2 cosine t, giving us tangent t is equal to positive 3 over 2. So then this time, tangent inverse of both sides gives us that t is equal to the tangent inverse of 3 over 2. So we go tan inverse 3 over 2. And this time, we get positive 0.98. Does this answer seem reasonable? Yeah, right? So this one does seem good. So this is going to be our answer, which is approximately 0.98, but we actually don't need the approximation. We can just use the exact answer. To find the position, we evaluate S of t at t equals tan inverse of 3 over 2, right? So we have both of these things in our calculator, right? So remember, the position function is saved as y1. So we go alpha, y1, and then we want to put in the answer that we had from the previous line. So we go second and our negative key down here. So we want to evaluate y1 at the answer from the previous line. And we get 3.605. So the maximum distance that it makes it away from equilibrium is about 3.61 if you go to 2 decimal places. And just make sure in WebAssign you round to whatever. Oftentimes I think it's either the hundredths or the thousandths, so round as asked. All right. So the key idea is we want to use these limits. So the limit as h goes to 0 of sine h over h. So at first glance, it doesn't appear that I would be able to use that on this because I have just an h in my limit, but in this function's limit, I have a 9x, right? So they don't appear to be the same. Well, h can really be any function. So that is really going to be our key idea. Well, I guess it can't be any function. It does have to be continuous. So h can be any continuous function. And then for our case, in this example, our h is going to be 9x. So then I need this to be h. So I want it to be 9x, but it's not 9x. What do I have? Just an x. So what is it missing? It's missing the 9, right? So in this case, we're going to use our property of fractions to help us out. So we have our 9x in here, and I have my x down here, but I have a fraction. And our property of building fractions says I can do the same thing to both the top and the bottom of the fraction, aka multiply by 1, right? Because if I multiply this fraction by 9 over 9, 9 divided by 9 is 1, and multiplication by 1 doesn't change anything. And now we're just going to regroup these things. Well, I don't need the 9 to evaluate the limit, so I'm just going to pull it all the way out in front of my limit. And then I'm going to be left with the sine of my 9x, which is my h, right? All over, in the denominator now, I have x times 9, so that's going to leave me with a 9x, right? So now these two guys are finally the same. So I can apply this rule, and what do we know that this limit is the same as? 1, right? The limit of sine h over h as h goes to 0 is 1. So the strategy in evaluating these limits is we need to turn them into something that looks like sine h over h, where h can be any continuous function. So in this example, we had a 9x inside the sine, so what did we need in the bottom? A 9x. So we multiplied the top and the bottom by what we needed to fix our limit, and then replaced it with what it was equal to, which is 1. So we're going to get 9 times 1, and the final solution is then going to be 9. So basically, for this type of problem, we're going to have to do some kind of algebraic manipulation to massage our limit into the form we need so that we can evaluate it. So let's go ahead and take a look at our next example. So a little comparing and contrasting. At first glance, it looks a little bit different. But once again, our strategy is going to be the same. We're going to do a little bit of algebraic manipulation. I'm going to split this actually into 2 fractions. I'm going to have sine pi over x over 1, and then I'm going to have 1 over sine 4x. And then we're going to fix these up independently. So if I ignore the second fraction for a minute, I have a sine pi x. So what do I need to have in the bottom? A sine pi x, right? So, but if I do it to the top, or to the bottom, I also have to do it to the top. So I'm going to multiply the top and the bottom by pi x. All right, so then that's going to give me sine pi x all over my pi x, and I'm like, yay! So that one's fixed, right? But now I've got this pi x sitting out in front, and I don't need to worry about it too much. And then I have this sine 4x. So what is it going to need? It's going to need a 4x. But the key thing we want to note is I already have the x, right? So I can bring that x in. I'm going to leave the pi out in front, though, because the pi isn't needed in there, right? What digit do I need inside that second fraction? Well, I have a 4x, so what do I need to multiply the top and the bottom by? 4, right? And so, finally, this leaves me with pi over 4. And I have my sine pi x over pi x times, and then I'm going to have my 4x over sine 4x. So now, finally, when I evaluate my limit as x goes to 0, I got my pi over 4, and then what does sine pi x over pi x equal to? 1. And what's the limit of 4x over sine 4x going to equal to? 1. So my final answer is going to be pi over 4. So once again, we just kind of massage this thing around by building our fractions to get the numbers that we needed. The one extra thing that was different from the first example is that we had that extra, we introduced an x, and instead of introducing two x's, right, we just pulled it in. If you do introduce another x, the algebra will work out. It just is a little longer. So there's another way to get there, and if you do it that way, it's fine too. It's not going to cause any serious problems, as mentioned. All right, now we've got this guy, and he looks like a mess, right? Let's see if we can figure this out. So far, we've only had to use one of our two facts. In this one, we're going to need both. So we had the limit as h goes to 0 of sine h over h equals 1, but we also had another limit. The limit as h goes to 0 of cosine h minus 1 over h, and that one was equal to 0, right? So let's go ahead and do the same thing that we did before. So we had in the previous example, we wrote it as sine 9x over 1 times 1 over cosine 7x take away 1, right? So we're going to do the same thing that we did before, and I'm going to do this one in the more lackadaisical way. I'm going to multiply the top and the bottom of this one by 9x, because that's what it needs. And what about my second one? What is it going to need? Well, I have a cosine 7x, so I'm going to multiply the top and the bottom of this one by 7x. So then, passing each of these in, I'm going to end up with the sine of 9x over 9x times 7x over the cosine of 7x take away 1. But I didn't use this guy, and I didn't use this guy, right? So those guys I will just pull all the way out in front. So 9x over 7x. And this is what I was saying now in this last step, what happens with those x's. They reduce out, and we still have our limit as x goes to 0. So now finally we evaluate that. We get 9/7 times the limit of sine 9x over 9x is 1 times, well, this limit is 0, so what would the reciprocal of that limit be? 1 over 0, and this is undefined. So this limit is dne, right? Because we ended up with 1 over this. All right. All right, so let's go ahead and resolve this. So let's break our tangent up into sine 4x over 1 times 1 over cosine 4x. And then we've got this 3x. So I'm going to put the x under the sine, and then we'll just put the 3 out in front. So the sine is going to need a 4 over 4, and the cosine's not going to need anything, right? So then we're going to have 1/3 times, and then we're going to have the limit as x goes to 0. Sorry, our 4 goes out here with the 4/3. The limit as x goes to 0 of sine 4x over 4x times the limit as x goes to 0 of 1 over the cosine of 4x. So that's one of our properties for limits, right? The product property. So now we're going to end up with 4 over 3 times 1 times the limit. Cosine is continuous and cosine of 0 is 1, so the cosine of 0, which is 1, so this gives us 4/3. All right.